Hi, folks. With this brief lecture, we conclude our discussion of Isaac Newton. So, we're in the middle of DeWitt's chapter here, and DeWitt, as we might recall from his discussion of Aristotle, oversimplified that a good bit. He didn't talk about Aristotle's four causes, he just contrasted teleological with mechanical causation. DeWitt presents Newton as bringing about something close to the realization of Kepler's clockwork model, a mechanical rather than a teleological physics. There is, of course, a great deal of truth in that, but I want to warn you off of some of the oversimplifications that might seduce you there. As we saw last week, Leibniz pointed out that lots of laws of nature look teleological. They make reference to an end state rather than any kind of pushing or pulling by which that end state is brought about. Leibniz's main example are least action principles governing the path light takes. So even in contemporary physics, it's not always clear that we've got a mechanical explanation for phenomena. We like to think we've got a mechanical physics, and to a very significant extent we do, but we don't have a perfectly mechanical physics. I briefly mentioned thermodynamics, which really comes into its own in the 19th century. Why does energy spread out? We do not have a mechanical model for energy spreading out. There is nothing about Newtonian or quantum mechanics underlying the behavior of, say, gas molecules that, so far as we can tell, forces them to spread out. They just do. Aristotle would call that a teleological explanation. It's an explanation in terms of an end state being attained. Leibniz is comfortable with that. Kepler and Newton don't like teleological explanations. But to a first approximation, we want to read off of the practices of science what it's committed to. So maybe that teleological explanation is shorthand for what will ultimately be a mechanical explanation, maybe not. Right now, we appeal to an end state without having a mechanism to appeal to. And that might be humbling from the standpoint of Kepler or Newton, but it seems to be the state of the science right now. The main point, though, concerns gravity itself. Gravity was seen as a kind of Aristotelian form, a kind of nature of things to do something close to a teleological explanation. Newton didn't want to see it that way, but Leibniz did see Newton's appeal to gravity that way, and for some reason. This reference to dormitive virtue, I should explain. In the 1700s, a French playwright named Molière makes fun of the Aristotelians. He has somebody sitting for his doctoral exam in chemistry. He's asked why opium puts people to sleep, and he triumphantly says, because it has a dormitive virtue, a sleep-inducing quality. According to Leibniz, gravity is a mysterious pulling virtue, a mysterious pulling quality. There is no rope provided. There is no contact force provided that is supposed to explain how gravity works. So DeWitt uses this example to try to remystify gravity for you. If you were asked to move a pencil without having any causal contact with it, without blowing on it, without shaking the table, you'd be at a loss as to how that's supposed to work. And yet, according to Newton, gravity causes everything to pull on everything else in the universe without any kind of contact. So it's a pulling, it's mechanical in that sense, but there is no mechanism provided for the pulling. And so it looked to people like Leibniz like as if Newton were much more Aristotelian than Newton would like to see himself as. Newton's most famous line about gravity is hypotheses non fingo. That does not mean I give hypotheses the finger, it means I refuse to form hypotheses. He doesn't claim to know what gravity is, or whether it's, scare quotes here, a real force. What he says is, here's how observable objects behave. Everything that you can observe is going to behave follow the three laws of motion and the universal principle of gravitation. So he doesn't want these things to be hypotheses, explanations that go behind the phenomena. He thinks they're inductively established generalizations, and that's why the Principia has this very patient approach. He says, it is as if there is an inverse square force between two objects here on Earth. It is as if there's one between them Earth and the Moon, it is as if there's one between the Sun and the Earth and the other planets. Since it is as if there is one everywhere, there is such a force everywhere. That is an inductively established generalization. You go from instances to local patterns to general patterns. Newton very self-consciously contrasts himself with Descartes, who wanted to use metaphysical principles to ground his science. Newton's science is supposed to be resolutely inductive rather than hypothetical. I'll say more about that in a minute, and we'll look at induction next week. Descartes, as we saw, derived the principle of inertia from the nature of God and the nature of motion. These are quasi-mathematical principles, deep metaphysical principles that he thinks are more secure than any experimental result. Newton was struck by the many mistakes Descartes made despite the high standards he set for himself. And so Newton rejects Cartesian claims about collisions and about empty space and the vortex theory of the solar system. And so he blames Descartes' reliance on principles that are prior to experiment. So he's when he says hypotheses non fingo, he is rejecting the method of hypothesis. The method of hypothesis, though, comes in at least two importantly different flavors. You can apply that term to Descartes. You have to be careful when doing so. And so there you look at the very nature of space or matter or motion or God and try to derive laws of physics from that. So you're supposed to get correct principles that are, as it were, in between observation and some kind of metaphysical or theological truths. A different and much more contemporary version of the method of hypothesis was proposed by Newton's contemporary Christian Huygens. As we saw in our in-class lecture on Newton, he's the main proponent of the wave theory of light, the first person to write a book on the theory of probability, a super important astronomer, mathematician, and physicist, and really a great rival in optics of Newton. The wave and the particle theories of light are going to be with us when we get to 19th and 20th century physics. Huygens thought that the way we do science is reminiscent of Popper from the very beginning of our class. Hypotheses are conjectures. They do not start off being probable. They are guesses, and they only have the status of guesses. Those guesses then get made more plausible when they survive testing, when they explain observation. Newton is opposed to that conception of the method of hypothesis as well. He wants science to be inductive. All we do is look at patterns and generalize those patterns. So, this question of what is gravity, what explains how things can pull on one another, Newton had hope for finding an explanation, but he would have to find an explanation in experience. For Newton, you can go beyond experience inductively. You can say this holds locally, so probably it holds beyond that. But you don't go behind experience, except in a few very local ways like Galileo did, this idea that there are bits of matter too small to see. Newton was on board with that. But he does not think that you have to explain what gravity is, come up with some mechanism that is not itself observable to explain the force. Why is gravity supposed to be legitimate, even though it's a mysterious pulling force that has no rope? Well, DeWitt suggests that Newton wasn't committed to it, that Newton was often an instrumentalist about gravity. It's just as if there was such a force. Nevertheless, Newton does sometimes say such a force really exists. For Newton, if you can quantitatively predict with a force, and if that holds up across a wide range of phenomena, that's how you do physics. So the question of what gravity is left physics around 1700 or so, after Newton becomes widely accepted, and it becomes part of metaphysics or theology. No physicist spent any time trying to worry about what gravity is. They took it for granted, and that's basically how your high school physics works. And so there is a loss of the kind of mysteriousness of gravity. Leibniz was right to be a little mystified. How can the moon, way up there in the sky, pull on the Earth without something like a rope? Newton's response is, I don't know, go ask God, but I will tell you that if you use these equations, you will put things where they are and not where they ain't, and you can drop large, heavy objects on people you don't like. So And a causal explanation is replaced within the Newtonian framework by precise quantitative predictions, and it changes the rules of science. That's one of the many fundamental things that Newton does. So, since Newton doesn't want to go behind the phenomena, the price he pays is silence about the causes or nature of gravity. He doesn't claim to know what it is. He doesn't think it's his job to know what it is, though he would love to. As Aristotle himself didn't always live up to his own standards, Newton preaches a resolutely inductive conception of physics, but he doesn't always practice it. He was very attached to the idea that light consists of little particles rather than waves, but that is going behind the phenomena. That is something like a hypothesis. Whenever he was pressed on that, he'd say, well, I don't propose to decide hypotheses. But in his practice, he was very committed to the corpuscularian theory. So I need you to focus on this distinction between two ways of going beyond the evidence. Inductively, you stay at the level of experience and say, this happens here, this happens there, this happens everywhere we've seen so far, so it'll happen everywhere. That's projecting a pattern farther into experience. A different way of going beyond the evidence would be hypothetically to try to explain what you observe by positing something you don't observe. You see a streak in a cloud chamber and you posit that there's a particle there. Newton does not officially endorse going behind experience, but he does resolutely go beyond experience. And that's why the structure of Principia has that repetition and pattern matching that it's got. Something like an inverse square law seems to correctly describe terrestrial motion. It seems to describe the moon and the tides. It seems to describe Kepler's laws. So let's inductively generalize and suggest that it describes everything. All right, that is the end of Newton. We'll be moving on to Hume's very philosophical post-Newtonianism, and then very quickly start getting to the 20th century in physics, where somebody like Einstein is going to bring the question of what gravity is back into physics. Thanks as always for your time and attention.